The concept of an eternal universe has intrigued scientists and philosophers for centuries. Various physical theories have emerged to explore this idea, suggesting that the universe may not have a definitive beginning or end. According to scientific theory and observations, in the beginning there was nothing. Then, approximately 13.8 billion years ago, the universe began its extraordinary journey with the Big Bang. This monumental event marked the birth of space, time, and all matter. But what exactly happened during this cosmic explosion? The Big Bang theory posits that the universe started as an infinitely dense point, often referred to as a singularity. This singularity contained all the energy and matter that would eventually expand into the universe we know today. As the universe expanded, it cooled, allowing particles like protons, neutrons, and electrons to form. Within the first few minutes, these particles combined to create simple elements, primarily hydrogen and helium. This process, known as Big Bang nucleosynthesis, laid the foundation for the stars and galaxies that would emerge later. But the story doesn't end there. Enter cosmic inflation, a theory proposed in the 1980s by physicist Alan Guth. Inflation suggests that, in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion. This rapid growth stretched the fabric of space-time, increasing the universe's size by a factor of at least 10^26. Why is inflation important? It explains several key observations about the universe. For instance, the uniformity of the cosmic microwave background radiation, which is the afterglow of the Big Bang, can be attributed to inflation. This radiation is remarkably even across the sky, suggesting that regions now far apart were once in close contact before inflation pushed them apart. Inflation also addresses the flatness problem. The universe appears to be geometrically flat, meaning it has just the right amount of matter and energy to prevent it from collapsing or expanding forever. Without inflation, the universe would likely have a curvature that would be noticeable on large scales. Additionally, inflation provides a mechanism for the formation of large-scale structures such as galaxies and clusters of galaxies. Quantum fluctuations during the inflationary period created tiny variations in density. These fluctuations later grew into the galaxies and cosmic structures observed today. Another prominent theory is the steady-state theory, proposed in the 1940s by Fred Hoyle, Thomas Gold, and Hermann Bondi. This theory posits that the universe is expanding, but new matter is continuously created to fill the gaps left by galaxies moving apart. As a result, the overall density of the universe remains constant over time. This theory contrasts sharply with the Big Bang theory, which suggests a singular beginning to the universe approximately 13.8 billion years ago. The steady-state theory gained traction for its philosophical appeal, as it aligns with the idea of an eternal universe. However, it faced significant challenges in the 1960s when evidence from cosmic microwave background radiation and the discovery of quasars indicated a changing universe. These findings led to a decline in support for the steady-state theory, but it remains an important part of the discussion surrounding the nature of the universe. Another intriguing concept is the cyclic Big Bounce model of the universe, which suggests that the universe undergoes infinite cycles of expansion and contraction. This idea has roots in ancient philosophies and has been revisited by modern physicists. The cyclic model proposes that after the universe reaches a maximum size, it will collapse back into a singularity, only to rebound and expand again in a new Big Bang. This cycle could theoretically continue indefinitely, implying an eternal existence. Quantum cosmology also offers insights into the nature of the universe. Theories such as the Hartley-Hawking no-boundary proposal suggest that the universe does not have a traditional beginning. Instead, it posits that time itself may behave differently at the quantum level, leading to a universe that is self-contained and eternal. In this view, the universe could be described as a four-dimensional entity without boundaries, where time and space are interwoven in a way that defies conventional understanding. Furthermore, the multiverse theory introduces another layer of complexity. This theory suggests that our universe is just one of many, each with its own distinct properties and laws of physics. In this framework, some universes may have always existed, while others may emerge from quantum fluctuations. The multiverse concept raises profound questions about the nature of existence and the possibility of an eternal universe. Despite these theories, the question of whether the universe is truly eternal remains open. Observations of cosmic expansion, the cosmic microwave background, and the distribution of galaxies provide valuable data. Yet they also lead to new questions. The nature of dark energy, which drives the accelerated expansion of the universe, adds further complexity to the discussion. Understanding dark energy's role may shed light on the ultimate fate of the universe and whether it will continue to expand indefinitely or eventually collapse. Philosophically, the idea of an eternal universe challenges traditional notions of time and existence. If the universe has no beginning or end, it raises questions about causality and the nature of reality itself. This perspective invites contemplation on the implications for human existence and the search for meaning in a potentially infinite cosmos. In conclusion, while various physical theories propose the possibility of an eternal universe, the debate remains unresolved. The steady-state theory, cyclic models, quantum cosmology, and multiverse theories each offer unique insights and challenges. As scientific inquiry continues to evolve, the quest to understand the universe's nature and its potential eternity will undoubtedly persist, inspiring future generations of thinkers and explorers. The exploration of these concepts not only deepens understanding of the cosmos, but also enriches the philosophical discourse surrounding existence itself.